So welcome back. We're continuing on our topic of looking at cache hierarchy and understanding different organizational structures and why certain cache organizations would perform better than others, and can we basically trace what we need to do um, with regards to activity in the cache. And that's where we left off on Wednesday. A relatively brief in-class exercise that did not go all that well due to technology limitations. But my pen is working today much better, so I finally figured that out after several months. So this is where we left off, where this was an example of a cache that has now two entry blocks, and it's described as bytes. The um, the homework question talks about them as word blocks. It's the same concept. It just matters what your smallest granularity of access is going to be. So 2 byte blocks here, which is very similar to our previous direct map cache. The main difference now is we have block indexes into the cache. So we're assuming that because it's 2 bytes per block, that row pointer we're looking up here, that index into the cache, corresponds to the entirety of that block. And we load the entire block. We load all the data in that block, in this case, those 2 bytes of data, and then we're loading that metadata as well. We're loading that or reading that tag bits, we're reading the valid bits, and we know the same condition is the same as before, that there is a hit when the tag matches our input tag. In this case, that's just 1 bit. It could be much larger. And our valid bit is also high. That's when we know we have something valid that we want to grab in our cache for our access. The main difference now is we've now added that mux. In this case, it would be a 2-to-1 mux. If it was a 4 byte block, that'd be a 4-to-1 mux. If it was a 64 entry or 64 byte block, that would be a 64-to-1 mux. But it's the same principle applied. You're reading the entire block, and then you're looking at those least significant bits of your address to figure out which of those entries in the block that I actually want. I know all the data is valid, so that valid bit and that tag bit apply to the entirety of that block because they all correspond to the same grouping of addresses or block of memory. We grab them all. We just use the mux to determine which one did my load word or load byte instruction actually need at the end of the day. So when we take that sort of toy example and just make it a little bit more realistic, here's a 4 kilobyte cache, which is much closer to what a real cache would look like in terms of size. And if we did 64 kilobyte or 1 megabyte example, it's the same thing, just more rows and more columns of our cache. That's the only difference here, right? So with a 32-bit address, you just have to continue to do that mapping of characteristics of a cache, how many bits I then need to select the various aspects of my cache, how many bits I need for the row pointer, how many I need effectively for the column selector for my mux, and then the remainder of those bits, no matter what, the remainder of those bits have to be used for the tag. That's the only way we can fully disambiguate between two different addresses that correspond to the same row in my cache is by having the remainder of that tag also stored in that cache to have that entire tag hit, that tag equality operator return in a correct result, that they are the same exact value. But otherwise, it's exactly the same. This is a cache with 1K blocks, each of 4 bytes, and with 32-bit memory addresses. And that tells you all you need to know about the cache. Also, that it's a direct mapped cache. But with that description, that gives you the entirety of the cache. That description gives you all of this and then gives you all of this as well. I would argue, once you have this, the address mapping, you're done. And that's what I talked about with the in-class example on Wednesday. You can draw out the cache. That can be very helpful to kind of trace things as they're happening in the cache. But that address mapping is what's critical. And then your addresses as they come in, you have to do your binary arithmetic or use your Windows calculator to convert the input decimal to binary and just make sure you know which bits go where. It was maybe trivial in the 4-bit address case where there was only 2 bits for the index. It's arguably still trivial in this case, or it's equivalent in this case. We have 1,024 blocks. That's a lot, but that's 10 bits. So we know that, we take the log of that, that's 10. So we know that there's going to be 10 bits for my block index. And we know exactly which 10 bits those are going to be because we have 4-byte blocks, so we're going to need 2 bits for my block offset. So those least significant 2 bits, because these are all going to correspond to the same block, so it's for spatial locality, right? For us to put things in the same block, we're doing it to take advantage of spatial locality. We want to put things that are near each other in our memory address space in that same block. That's the whole point of having this wider cache organization. So if it's a 4-byte block, that means 2 bits. Then there's 1024 entries, that means 10 bits. And then there's a 32-bit total address. That means the remainder, that which would be 20 bits, would be stored as our tag here. And it's otherwise exactly the same as that little 4-entry cache that we had on the previous slide. Larger mux, wider tag comparator unit, otherwise completely identical. So we can do that. With that larger cache, if we had an arbitrary address come in, we'd use the binary for it. We just convert it to binary. And if you don't want to do it by hand, I get that. So just convert it in your calculator, or I'll just provide it as a binary address. Certainly on an exam, I'm not testing your ability to convert 6146 to the equivalent binary string. So I'll just give it to you in binary in that case. But based on that description of the cache, 2 to the 2 byte blocks, 2 to the 10 number of blocks. We grab those 2 least significant bits, that's our block offset. The next 10 bits are going to be our index into the cache, and the remainder of it is going to correspond to our tag. I think I just covered that here, right? So for that incoming address, we have the tag, which is those upper bits. Those middle bits, in this case, are our index into the cache, and our least significant bits are going to be our offset into that block. So for that incoming address of, what was it, 6146, it's going to actually correspond to, just based on how the binary arithmetic works out, it's going to correspond to the 512th entry in that cache. Index of equal to 512 with a tag of just all zeros with just 1 in the least significant bit there, and it's going to be offset 2 into that block. So this is location 6146. So based on how our spatially aware cache works, we also would know exactly what else is stored in that block. All the other aspects of the address are going to be the same for every location stored in that same block, because they all would have the same tag, the same valid bit. They would have the same corresponding index because they're all stored in that same exact row. The only thing that would be different between those entries in the cache would be the block offset. So taking advantage of spatial locality doesn't mean that when we request 6146, we would then grab 6147, 6148, and 6149. It doesn't necessarily mean that. It means we grab everything that corresponds to the same block location in our memory. So if this one is 6146, we should know what's in those other locations. And it's not the next 4 or the next 3 after that, right? This one is 6146 because it has a block offset of 2. We would then have the block offset of 3 stored here. That's 6147. But then the other 2, this would be 6145 and 6144 is what would else be stored in that same location in the cache. I got to chew on your question that you asked in the chat there. Yeah, so usually, so we would have from the cache's perspective, and this semester we're not talking about virtual versus physical addresses at all. From the cache's perspective, it's just an address, and it doesn't necessarily know at all where that location truly belongs, where its final resting place is for that location in memory. That's going to be application specific. So generally, the cache just knows this is data at this location, and my process running on my processor needs it right now. Keeping track of where things ultimately have to reside is a function of your program, and it's a function of your operating system at that point. We don't do a load word directly to our hard drive, right? There's going to be a kernel level driver usually that will have a routine that takes chunks of memory at a time and writes them to disk. And that's ultimately still loads and stores, but it involves circumventing the cache and things of that nature. Hopefully that's a topic that gets covered in 308 or in ComSci 352. So that's the rest of the block. So I think we covered that. If this one is 6146, spatial locality doesn't mean you take the next 3 things. That would be maybe ideal if a cache could organize that way. But because we're just grabbing that block of memory, that block corresponds to that neighborhood of the location we grabbed, and it just corresponds to what else would have the same exact block index into our cache. So it's possible. It depends on how you define your spatial locality. That this one would be a miss on the cache because we have to bring in that entire block into the cache. Maybe this next access of A of I++ would be a hit, but then we'd have a miss again when we want to grab 6148. Because even though we have this 4-byte block size in the cache, that doesn't mean we've guaranteed the next three things are going to be in our cache. There is no guarantee of that. Perhaps in the steady state, though, it would work out pretty well. If we do a of I plus plus for a very large loop of n, which is kind of sort of what your homework 10 final question was trying to get at, um, it should work out pretty well in the steady state. That we'll still get misses, but a large number of our requests are going to hopefully then be hits. So not a transition here, but continuing on this topic, and there was already some questions on Wednesday about it, so we definitely do need to cover it. There's a definite disadvantage of our direct map cache, independent of the width of that cache, how many bytes are in a block. Just considering blocks themselves of any size, the main disadvantage of it is that we have this very simple mapping of main memory addresses to our cache addresses, and we have this issue of sort of accidental aliasing, right? This is going back to our somewhat toy example where we had 16 entries in our main memory and 4 entries in our cache, and we saw that. That was our color coding, right? That both 2 and 6 and 10 and 14 all correspond and all map to that same location in the cache. That's that's what we mean by direct mapping. So that's not something that we avoid via this direct map cache. But if our access pattern happened to fall into that unlikely combination of repeated locations that all correspond to that same location in the cache. So if our access string, as we talked about those, was 2, 6, 10, 14, 2, 6, 10, 14, repeated ad infinitum, right? That would be very poor performance on this cache. We would keep replacing that same exact location in the cache over and over and over and over again. And in fact, we wouldn't actually use any of the other locations in our cache, right? It would sit empty effectively. It would be effectively a waste of our time associated with, waste of our space that we've dedicated to that cache. We have room for 4 blocks just because of our particular access pattern, and this is a very synthetic case, but because of our particular access pattern, we're aliasing. We're having conflicts where multiple addresses are all corresponding to the same exact location. We're not really using our cache very effectively there, and it is hard from a programmer's perspective, to know if that's ever going to happen or not. In a brief aside, I mentioned that homework 10 question a couple of times here. I'll be honest, I wish we had more of those questions in this type of class. They're hard to do. They're hard to come up with synthetic examples that you can both complete, and then we can actually trust what the compiler is going to generate. So going back to that homework 10 question, where it asked about a double nested for loop, right, and a 2-dimensional array. What that loop itself was doing didn't really matter. So the code was just multiplied by a constant. So it could have been any sort of thing. That was just an example of write some code that iterates through that 2-dimensional array. And the order in which we iterate through that array matters a lot. And it matters a lot specifically for this reason of taking advantage of spatial larger block sizes in our cache, for taking advantage of this feature in our cache. I don't have the code in front of me, but there's this loop that does an I loop and a loop that does a J loop. And we have this 2-dimensional array A that has our rows and columns. And you can visualize it as a 2-dimensional data structure. We know ultimately that corresponds to sequential accesses in memory, right? Back when we were learning about load word and store word, we did that math for us, right? We did that math and converting it to assembly. Our data structure is 2-dimensional to help us as the programmer work with data and write code. In terms of how that ultimately maps to memory, those are linear addresses. And it does tend to be programming language specific, but almost all programming languages, it's not a dumb question at all, actually. Almost all programming languages do what's referred to as sort of row major ordering of data. It's not all. Fortran does it column by column. There's some other examples where it's not guaranteed by the programming language, and that's an implementation specific feature. But in C, at least, that's about as high level we get in this class, your data, if it's a multi-dimensional array, is laid out by row major order. So it does the entire first row is my first block of addresses, then my entire second row and my entire third row. And you can apply this concepts if you have 3-dimensional and 4-dimensional data, but just sticking with 2 dimensions, we laid out row by row by row in memory. So the address of A of 1 comma 0 is next to the address of A of 0 comma n. So the last entry of the first row is right next to the first entry of the next row. And that would have a pretty big impact in terms of the spatial locality of the program, right? As we lay things out in memory that way, and as we then iterate through our memory that way, where we access A of 0, 0, then A of 0, 1, then A of 0, 2, etc., right? We do the inner loop, the J loop first, then we do the outer loop, the I loop last. That is accessing things in our code row by row by row. That's going to lead to consecutive addresses in memory. You're going to have a lot of, add I plus 4 in your code if you looked at the assembly for it. And that's going to lead to good performance on a cache for spatial locality reasons. This will be A of 0, 0. It'll be a miss, but then we'll hit on A of 0, 1, A of 0, 2, A of 0, 3. How much you miss and how much you hit depends on your cache and depends on some architectural features that we don't know. But that generally would perform pretty well. When you then flip those two loops around, and now it's the J is the outer loop and I is the inner loop. Now what are we accessing? We're accessing A of 0, 0, then A of 1, 0, then A of 2, 0, etc. We're going column by column now. Our memory is still laid out row by row. So we're accessing whatever this location corresponds to A of 0, comma 0. Next one is A of 1, comma 0. That's a whole n bytes or n entries later in memory. It's not spatial at all. It's not near at all. So that's going to presumably be multiple misses. And it's going to probably keep missing. So presumably when you swap the order of those two loops, the one that is doing column by column accesses should perform much worse than your one that does it row by row axis. I've run this experiment in the past, not for this homework question, but for other experiments. And generally that is the case, that you can see the impact of reordering your loops if you accidentally do it the wrong way. What seemed to be coming up for a couple students last night, and I have also seen in the past, is that under certain assumptions, compilers can be smart enough to detect when that's about to happen. That you have written code that iterates effectively in an inefficient way, that does it column by column versus row by row, and it'll actually generate code for you that instead iterates row by row. Because from the compiler's perspective, well, certainly for this code, none of that updating A of I changes program state. Perhaps if we added some print statements, it wouldn't be able to reorder it for us because that's changing the correctness of our code by reordering those loops. But we have a function, we call it, don't do anything with it. Compiler has a lot of flexibility in terms of how it does that optimization. And we may have seen that for a couple of cases yesterday evening as you were working on it, that it was clever enough to reorder loops. By and large, it doesn't. But compilers, if you lit them, will be extremely aggressive in terms of determining what it can do with your code, what it can basically just remove entirely. We've seen it with VHDL compilation this semester. C coding is really, the compilers are applying very similar principles of how live is this code? Does this code need to even exist that you've specified? And if the answer is no, either just delete it. If it can be significantly changed, do whatever is feasible, whatever is correct in terms of doing that modification. But I think for the vast majority of you, you should have seen different performance in the row major order or the row by row code versus the column by column code. Okay, let's context switch back here. So direct map caches are fun. They're nice and simple. Our address mapping is just really straightforward. Grab the appropriate bits of our address and figure out what to read from the cache, and then mux out the block the byte we want out of the block. The disadvantages, as we see here, with that access pattern of 26262, and you can come up with all sorts of access patterns that would do very poorly on this cache. It's relatively straightforward to come up with an access pattern that has 0 hits. It takes a little bit more thought to come up with access patterns that have hits on a cache like this. That's the downside of our direct map cache. You can think of direct map as one extreme of cache organization. The other extreme, or the flip side of that type of cache organization is referred to as a fully associative cache. That's just a term of art in cache organization. It's just like remembering direct map. Just remember that term of fully associative cache, where in the fully associative cache, there's no address mapping whatsoever. That's the other extreme. Direct map is Every memory address has exactly one place it corresponds to in the cache. The other extreme is fully associative. Any address can go anywhere in the cache. So we don't force any memory address into any one particular block. So when it's time to fetch something from our fully associative cache, we have to check the entire cache. So just like I mentioned, and we already started to see that there's maybe some downsides of having a direct map cache, that it's still a valid cache consideration, and for certain circumstances makes a lot of sense. We can maybe already very quickly see maybe the downside of a fully associative cache. Having said that, you will still see those in certain configurations. But that's the other extreme. Instead of having only one place you ever have to check, but having the what do you want to call it, the aliasing issue, the unnecessary conflict issue of 26262 in your direct map cache, you would not have that problem in your fully associative cache because you could put 2 wherever you'd like to put it and you could put 6 wherever you'd like to put it. You still then have to make a decision of once my cache is full, which given the sizes of caches versus the amount of memory accesses a typical program would have, right? Your cache can store thousands of things. Your memory, your program is going to access millions of things. Your caches are going to fill pretty quickly. So for our fully associative cache, we would then need to have some sort of cache replacement policy. And discussing those becomes an important topic for understanding how caches work in practice. We talked about least recently used as being kind of the default cache policy for a direct map cache. You can also apply a least recently used policy for a fully associative cache. The difference now is you actually have to keep track of it. You have to actually know via some mechanism which of the blocks that I want to access are actually the least recently used. So for 2626262, a fully associative cache would perform extremely well. For 268, 2610, 14, let's say 18, it has to have some way of keeping track of 18 comes in. We want that in the cache. Temporal locality tells us we should have that in our cache. Which of those existing 4 entries that are in our cache are we going to get rid of? And that least recently used policy is something we're already kind of doing for the direct map cache, but we didn't have to do anything to support it in the direct map cache. It was just kind of fundamental by the nature of you just get rid of whatever's there, overwrite whatever's there. That's one way of doing a least recently used policy. Whatever happened to be in that location, just overwrite it, get rid of it. For a fully associative cache, because we can now put this anywhere, we have to have some way of keeping track of which entry in the cache should be our odd man out, odd one out, the one that is our imposter in the cache that we don't want anymore. So we get rid of that one. And there's ways to keep track of that that don't involve storing timestamps or doing sorting. It is kind of sort of a heuristic for doing that without all the overhead associated with tagging every single entry in the cache and literally knowing the truthfulness of which one is truly the oldest one. There's a ways we can relatively efficiently keep track of that information, but that is another cache parameter that as we design our caches and put in our system, we tune that parameter to determine how much extra storage overhead do we want versus how accurately do we want to be able to keep track of least recently used information for our cache. Kind of, sort of, right? The problem is the overhead in terms of how we can implement that. If I told you to write, like, let's say, a software emulator for an associative cache, and not just the fully associative cache, but any set associative cache, and to write a software structure that keeps track of that information, you could do so. Stack would be a little tricky because we have random access here as well, right? So which one goes to the top of the stack is kind of tricky. So you'd have to do random lookups and determine. So there's priority queues. There's ways you could implement it with precise information. We want to implement it in a relatively efficient hardware managed way. So there's relatively straightforward ways we can do it, but they do tend to involve some sort of accuracy and performance trade-off. We won't explore too much of that in terms of the design of our caches. I'll just share a couple examples of what that would look like in practice and what that does look like in real world caches. Backing up here, and by the way, you guys are active today. I appreciate it very much. I very much thank you. Um, Backing up to what it would look like to implement a fully associative cache. And again, I mentioned our direct map kind of, 4 entry examples are definitely toys, but direct map caches are a real thing. They're not always the best choice. Likewise, a fully associative cache is very expensive to implement, but are very much still a thing. Just under certain assumptions, they may make sense for a particular implementation. The difference then between them is in the direct map cache, we know exactly which entry we have to check for validity. Based on our block index, we grab that entire quote unquote row of our cache. That is the tag bit that we have to check. It's either a hit or a miss based on that information that we've grabbed here. For our fully associative cache, we look at our address mapping now. This is somewhat orthogonal to the size of our block. We could still have a block offset and can still have those muxes, but ignoring that for just a moment here, for our fully associative cache, because our location can go anywhere, effectively the entire address has to be our tag. We have no way of knowing where 2 went in the cache, and no way of knowing, at least a priori, where 6 went in the cache. We have to check the entire cache. And we have to do it efficiently, right? This doesn't make sense if we have to do some sequential search or some very long, painful operation to do this. We have to do this really efficiently for this cache to feed our pipeline for it to be worthwhile in the first place. And so you see a structure that, what that looks like in practice really can depend, but at least logically what it looks like is for every single entry in the cache, you're now basically replicating that direct mapped cache structure. You're treating them as n independent little direct mapped caches, where for each one you're having to check, is this my tag? We don't know where it went in the cache. We're checking every single entry in the cache, presumably with some amount of significant parallelism here for this to be a worthwhile thing to have. We could do it sequentially. You could build a sequential circuit that does this, that basically loads each one in time. That would be very painful to implement as well in terms of the performance of the cache. We're trying to do as much as possible in one single go here. Read the entire thing. Hopefully, one of those would be a hit. It's actually, and to be honest, that's not quite precise, right? So this OR gate is correct in terms of telling us that there is a hit. We would still need to have these results, this kind of local hit result, driving some sort of mux to give us the final result. That not only was there a hit, here's the actual data that you requested. Because I need to know not just that there was a hit, I need to know which one of these was a hit. But conceptually, it's the same idea. So that's fully associative, and it is presented as something of an extreme. If direct map is one place for everything, fully associative is every place for everything. If those are presented as two extremes, maybe you can start to see where that in between kind of way of thinking about it would be. That's referred to as a set associative cache. That's the more generic terms. And often you will see a cache described as being, we'll say, for example, a two-way set associative cache versus a four-way versus an eight-way set associative cache. Before I even get into the details of this, if we think of direct map cache as having one place anything can go, another term we could use for it would be a one-way set associative cache. That is what it is. That's the extreme. That is one place for everything. And it's a little harder to use the right term for it. Would be a n-way set associative cache would be our fully associative cache for n total entries in our cache. That is the other extreme. In practice, what we tend to see are 2 to the x way set associative caches, where x is 1, 2, 3, 4. I don't see more than 16 way, and 4 and 8 seems to be the most common combination here. So you'll see a 4-way set associative cache or an 8-way set associative cache. What that means in practice, we'll talk about in just a second here, but don't overthink it. If it's a 2-way set associative cache, it is basically 2 direct map caches where we have to check both, right? Fully associative cache is sort of unworkable because we have to check everything. Direct map cache is workable, but has some issues with keeping enough temporal locality in our code. 2-way set associative cache works as a nice in between. There's 2 places we have to check. That location 2 in memory and 6 in memory have 2 possible places they could be. That could be thought of, at least for that toy example, as the best of both worlds, right? 2 could be in one of 2 places. 6 can be in one of 2 places. We have to check both, so it's maybe twice the overhead, but now we get the upside of the associativity of the cache. We can have both 2 and 6 in the same cache at the same time because we have that little bit of flexibility with where we put things. And that's what the 4-way set associative gets you. It's 4 direct mapped caches, effectively. And so there's 4 places we can put something. You can start to see there's a trade-off involved. How much flexibility we have in terms of where we put things in can put things in the cache, and how much overhead we have of that sort of comparison and checking hardware we have associated with that cache here. I do want to make sure, and sometimes the textbook doesn't do that great of a job with that, is that it's not a free thing to increase the associativity of the cache, right? You are effectively doubling the size of your cache when you go from a direct map cache to a two-way set associative cache. Well, if it's a homework question, the question has to be very explicit what that means. Because if it doesn't say so, and that the assumption is you're just literally doubling the direct map cache to make 2 of them, yes, that set associative cache is always going to be better. But presumably, in a real system where we're evaluating trade-offs of our cache design, we're deciding based on a total storage budget. I can store 16 kilobytes in my cache. One way or the other, that's how much SRAM real estate I have, transistor budget I have for my cache for this design. How do I want to organize it? So it could be a direct map versus a two-way versus a four-way set associative. But this picture, I think, does a better job of illustrating what that trade-off would actually mean in practice, in which you could have a direct map cache versus a two-way set associative cache, but for it to be a fair comparison, for it to be an actual trade-off you're exploring, that two-way set associative cache would have only 4 different blocks that you could then access in the cache. Because for this to be a fair comparison, they have to be roughly the same sized cache. If you just literally copied and made 2 of these, that would be fine. That would be a much bigger cache, but that would be twice the size of that particular cache. So the textbook doesn't always do that. I think that's a more fair comparison to make between our direct map, two-way set associative, four-way set associative. The fully associative would also be an 8-way set associative for 8 total sets in our cache, and that would be just a single block where we can put anything anywhere. So direct map, everything goes in one place. Two-way set associative, everything has 2 different places it could possibly be. So for index 0, there's 2 places I have to look. For index 1, there's 2 different places I have to look, and so forth. And for four-way set associative of the same size, now we have definitely fewer sets, fewer total unique storage locations in my cache, but now there's 4x the flexibility of where something could be found inside that cache. But these are all 8-block caches. These are all storing the same amount of total data in our cache. They would have slightly different overheads because the tag bits would be slightly different, etc. for them. But otherwise, they're holding roughly the same amount of information. This would at least be a fair comparison of which cache performs better for my application. How much flexibility did my application ultimately wind up needing, or was this sufficient for my application? We can usually never say. We usually have to measure. We usually have to run code, evaluate benchmarks, and determine for the type of applications we're interested in running, which type of cache organization or mixture of organizations makes the most sense for that particular cache. But otherwise, nothing has really changed in terms of how we're accessing this particular cache. We still have our particular M-bit total address. Assume that 32, that's fine. We still have potentially these wide blocks for our spatial locality. So that is an orthogonal concept. Whether we want a certain width of our blocks and how much width we want, that's not free lunch either. We still have to pay for those transistors no matter what. But that is a separable concept of how wide we want each block to be. And we have to have the appropriate number of bits to mux that block when we actually load what we are interested in. And now there's just this set index, which you really don't have to overthink. It's the same concept. How many sets are now in my cache? It still is the same as, if you want to visually lay it out, how many rows are there still in my cache? It's still the same concept. If there's 1,000 sets in my cache or 1024 sets in my cache, like we saw before, I called them blocks before. Now there's technically maybe 2x or 4x the number of blocks, but the number of rows is still the same. And we're still would be then using those middle 10 bits to determine which set am I interested in potentially reading from. The difference now with a 2-way, a 4-way, an n-way set associative cache, there's multiple of those that I have to read from and determine which one was actually the information that I was actually storing. But that's it. So when you hear that there's a 2-way set associative cache or a 4-way set associative cache, you're doing the same exact arithmetic you're having to just check more things to determine if there was a hit or not in the cache. This visualizes it somewhat well. So for the same particular address breakdown where there's 16 bytes per block for this example here, okay, I'm telling you the homework question, the exam question is telling you there are 16 bytes per block here. That is instantly 4 bits for my block offset. Let's set aside 4 bits that are just for that. That's constant across all these cache organizations. So if we're told also there's 8 total blocks in our cache, that's an important piece of information. For it to be a fair comparison between cache architectures, as I mentioned, you should have roughly the same amount of storage in each cache. So if there's 8 blocks in our cache, the organization of the cache then tells us where exactly those blocks are going to be located. We've done the direct map cache example for that. There's 8 blocks in our cache. Those next 3 bits are going to be used to figure out which row I'm grabbing. If it's a two-way set associative cache, there's actually now going to be just 4 sets in a cache for 8 total blocks. I would then only use the next 2 significant bits to figure out my row in the cache. And then finally, if it's a 4-way set associative cache, I'm going to have 2 sets, 4 ways or 4 blocks here, but 2 sets. I'll just have a single bit to tell us which of those I'm actually interested in accessing. And if it was a fully associative cache, there'd be 0 green bits here, right? I'd have to check them all. I wouldn't know at all where it would possibly be located. So that's the main difference. It's not clear to me if this way of visualizing it is easier to understand the address mapping, or I'll be honest. For me, I think it's easier to look at the layout of. Let's go forward just a second here, of this version of the layout. It depends. It depends on how you visualize things and how you can work your way through the binary math to figure out what's happening here. This is my own bias that I find this layout a little bit easier to visualize what's happening in the cache for a set associative cache, because I do just think of them as for a two-way set associative cache. I think of it as there being 2 copies of my direct map cache, and they're doing the same thing. So for my two-way set associative cache, I have a certain number of bits that are going to dictate my index. And once you have, again, this address mapping, you're home free. You've got this. You know what this cache needs to do. You can answer any question I give you about a cache if you have that address mapping. But given that index, the difference again is instead of just reading from my single direct map cache here, I'm going to concurrently read from both for a two-way set associative cache, or from all 4 for a 4-way set associative cache. I'm going to read from all of them at once. I'm going to read from the same row because it's the same index. And I'm going to basically do the same exact operation twice. I'm going to determine which, if any of those, corresponded to a hit. They'll have 2 different tag information, right? Address 2 and address 6 and address 10. They'll have the same index, but they'll have different tag information associated with them. Only one of them, at most one of them, would be guaranteed to be a hit in our cache. So we look up 2 in the case of two-way set associative. We'd look up 4 in the case of four-way set associative. In fully associative, we look up all those entries, and we determine if there was a hit in any of them. So our actual overhead of doing this, if you think of it as a logical layout, it's roughly the same amount of storage, right? We have maybe a different way of encoding things like least recently used information versus a direct map cache, but it's otherwise the same amount of bits by and large. We have a little bit more logic for our comparators and for our muxes and our gates and things like that. But if you think about the size of these caches, adding an extra 20-bit comparator is peanuts, right? It is nothing. It's compared to the overall transistor budget we have for this particular cache. For the fully associative cache, that would not be the case, but for the direct mapped and two-way set associative cache, those comparators are comparatively tiny. They're very small. So the overhead of doing this is reasonable. It gets us some of the way towards flexibility of where we put things in the cache, with most of the flexibility and simplicity of our direct map cache. I skipped ahead just to show that these previous pictures of where you're putting things in the cache. This is an accurate layout of what is happening here, that you have for the same number of total blocks, you have fewer sets in the set associative cache. and so on. As you increase the associativity, you will have fewer and fewer sets. That is correct. This is a logical way of breaking it down. It is completely correct. For me, just when I'm visualizing what's happening in the cache and I want to draw it out, I would draw it out this way. I would draw it out as first, figuring out my address mapping, and then, you don't have to draw all the detail, right? But drawing out enough of the detail that I know, okay, this is a two-way set associative. I've got two chunks of things that are kind of independent from each other. So I think that's important. And if you do it that way, the rest is just details of knowing exactly what my tags are going to be, whether we have valid data or not in the cache at a given time. So that's why I skipped ahead. I thought that was important. But the question's already come up, and it is important also to cover, what does it mean in terms of things being least recently used? And so you guys are getting to it, or you're getting ahead, which is good. We're saying that for our particular replacement, when there's a miss, and let's assume that this green block is already filled, and I want to put a third thing in that green block. 2 and 6 are already in there. Now I'm requesting 10. Then the question becomes, how do I keep track of that? How do I keep track of which one I should get rid of? Temporal locality tells us we should get rid of whichever is stalest, whichever one was least recently used. That's all that means, right? That's our principle, that if we use something, we're likely to use it again in the future. I think a direct corollary of that would be if we haven't used something, we're less likely to use it again in the future. They're directly relatable topics, I think. That's why least recently used generally makes sense for a cache replacement policy. There are other approaches that can be taken. For a two-way set associative cache, and I think a couple of you are already getting to that, we don't really need to keep track of timestamps or anything like that. A single bit of information for a two-way set associative cache would be sufficient. A bit of information per set. Because there's only two choices. Either this one is least recently used, or this one is least recently used, right? It's one or the other. Or, there can't be a tie, right? There's a load that comes to one before the load comes to the other. One of them is more least recently used, is less recently used than the other. So a single bit should be sufficient to store that. We don't really need to know how less recently used it is. It's a binary thing. This one is less than the other. And that's something that we can keep up with or keep track of relatively simply. It's ultimately just going to be a single bit here. Let's walk through as our final thing for today. We got started a little bit late. Let's walk through this exercise, and breaking out into teams did not work well at all. So let's not even try. So this is both a two-way set associative and a fully associative cache, because there's just two blocks in the cache for this example. We can walk through a more complicated example after we do this one today, maybe on Monday. But we start with just two blocks. So we have two locations in the cache, a left and a right, or a 0 and a 1 location in the cache. And our addresses as they come in can go to either of those locations in the cache. Pull this up here. So we can start with a default of that one bit of storage saying 0 is the least recently used entry. There's nothing in the cache. It doesn't really matter. We assume A and B are different. They would go to distinct blocks. That's fine. They're different addresses here. Let me walk through the first couple, and then let's walk through the remainder ourselves. So if we start with A, our cache is initially empty or invalid, or just some default value for our least recently used information saying block 0 is least recently used. Whoops. We'll do it with the pen. I did not do it properly. After we would have accessed A, well, what would happen? A comes in. We want to request A. A would then get stored in the cache in one of those two locations. We just have to have some default value. Maybe it's a tiebreaker scenario. We would then have A in the cache here. Take my word for it. We would have A in the cache there. The main difference now, if this was a direct map cache, we would be done. A came in, we put A somewhere, we are done. The main difference now is we can actually also then update that least recently used information. 0 happened to be what we had tagged the least recently used information as. Well, it's not 0 anymore because we did just use that location 0. It's now very recently used. Even though it was a miss originally and we had to go put it in the cache, it was very recently used. So our least recently used, there's only two options here for a two-way set associative cache, would now be the other entry. B comes in. It's a distinct address. That this example only makes sense if they are different addresses corresponding to different locations in our cache. B comes in. Do we put it in the left or in the right? Let's walk through a couple. Let's do a couple of these, and then I'll get your buy-in here. That's fine. B comes in. It's going to replace the least recently used, which is this one. And then that's the whole point of having. I hate this. That's the whole point of having a least recently used cache. Excuse me, a set associative cache. That's the whole point of having one in the first place, right? If I have to alias A and B on top of each other, well, I have a direct map cache. There's no point anymore. A and B can both fit in the cache at the same time because we have that flexibility with where we put things. We put B over here because this is what it told us. Hey, when you have to replace something, put it in 1 because that's our stalest data. But now that we've put B in there, we now would have to mark 0 as our least recently used because it is. Because the most recent one we used was 1, was the one that the right-hand side one we could put it. If now A comes in again, how do we change our cache? Now I think you should be able to tell me. Yep, the cache stays the same. I'll still draw it if I can. But now the main difference is it was a hit in the cache finally, right? So A, B, A, we have a hit in the cache because A is still in the cache. That's why we have our two-way set associative cache. Thank you. And now the only thing that's changed is because we've now accessed A again, B is now our least recently used. So in terms of how we would implement it, I think you could start to see that, right? Based on whether there's a miss or a hit in the cache, you could determine based on where we either read something from the cache, where our hit was located, or based on where we just put something in the cache, we can then update our cache accordingly. So this is kind of an unfortunate example in the sense that it shows that even with a two-way set associative cache, we can't really keep the cache entirely happy all the time. Now C comes in. Is it going to be CB or AC? That's right. Okay, I think we're getting it here. It would be AC 0. That's right, because we put C in there, and now we have just used tag 1. Now B comes in, and now you can see where you get that real flexibility in the set associative cache, right? I know we have to go. We'll end it here. But this is something that we would never have seen in our direct map cache, right? In our direct map cache, there's one place for everything. Everything goes in one exact spot here. But we've now just seen this memory location B was originally quite happy in the rightmost location in our two-way set associative cache. Um, and now it's found itself in the other location in the cache. But that's what we have with this cache architecture. We have that flexibility with where we could put things. Our LRU information was alternating because of this example being a little silly. I'm trying to think if it's ever going to stop alternating. No, that's just the example we have here. But if my access pattern was A, B, 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 the LRU wouldn't change, right? Because something is more. Yeah, that's right. Because something is more active and being used more recently. We're not actually keeping track of the most recently used thing. We're keeping track of the least recently used thing, and that wouldn't change. We would have one very active location in our set and one very stale, least recently used location in our set. That's just side effect of this example that it's kind of fluctuating between one and the other. I think in the interest of time, we do have to leave things for here for today. I have my office hours today. If anyone wants to stop by and say hello, you don't have to. Otherwise, this is our final kind of weekend of the semester for this class at least. So good luck and keep making progress and put some time in. And I think it's going to turn out just fine for you. So enjoy your weekend. Otherwise, I'll see everyone on Monday.